So now how does all of this come together when we're working with actual reactions? So if we're talking about calculations for actual reactions, especially in terms of something like predicting how much product we can form, four basic steps. One, make sure our equation is balanced. Two, find the moles of the reactant. Once we've got our moles of reactant, we can convert to moles of product, which we'll show how we do here in a moment. And finally, we can convert from moles of product back to mass of product. And so this is going to allow us to determine in any situation that we're dealing with, if we have this much starting material, how much product will allow us to form. So we're going to use this reaction that we balanced in the previous video. Potassium plus oxygen react to form potassium oxide. So we might ask here, if we start with 2 grams of potassium, assuming that we have enough oxygen, and that's something that we'll talk about later on, what exactly that means. But how much potassium oxide can be formed from 2 grams of potassium? So our first step, as we said, is to balance the equation. We've already done that. So that means our next step is to calculate our moles of potassium. And we can do that using the mass of potassium on the periodic table. So 2 grams of potassium, 1 mole of potassium is 39.1 grams of potassium, or 0.0512 moles of potassium. Our next step is we need to determine moles of product. And the moles of product is why we have to balance our equation. Because by balancing this equation, we now know that 4 moles of potassium will form 2 moles of potassium oxide. And so that's what will make our conversion factor here. So moles of potassium go on the bottom because that's what we're trying to get rid of, and moles of potassium oxide on top. And so we find that this reaction, again, if we start with 2 grams of potassium, will form 0.0256 moles of potassium oxide. So then our final step is to convert from moles of potassium oxide into grams. Again, we would calculate the molar mass of potassium oxide, which in this case is 94.2 grams per 1 mole. And as a result, we find that we would form 2.41 grams of potassium oxide. Now, we're going to ask a second question. How much oxygen do we need? So we do this the exact same way that we did the previous calculation. We take our moles of potassium oxide, or I'm sorry, our moles of potassium that we started with, so 0.0512 moles. But now we're going to convert from moles of potassium into moles of oxygen. How many moles is that? That's again our stoichiometric coefficients. There's no number in front of oxygen, so we know that that's 1. So 1 mole of oxygen, 4 moles of potassium. And then we can convert moles of oxygen into grams. 32 grams of oxygen is 1 mole, or 0.0, I'm sorry, not that, 0.410 grams of oxygen. All right, let's do another one. C3H8O plus O2 gives us carbon dioxide and water. And so the question we're going to ask is, if we have 11.3 grams of C3H8O, how much oxygen is needed? And then we're going to calculate the amounts of each of the products that would be formed. Now, before we can do any of this, we need to balance our equation. So that's what we're starting with. If we put a 3 in front of CO2, now our carbons are balanced. It does unfortunately unbalance our oxygens, but that's what happens many times. We can then balance hydrogens by putting a 4 out here. Again, that's going to change our number of oxygens, but it makes it 10, which is going to be almost as easy as we'd like it to be, because we have 3 on the left side. Now, if we make this oxygen here 9 halves, does that get us what we need? It does. That gets us to 10. Now, again, if you don't like the fractions, just multiply everything through by 2. And as long as we've done everything correctly, it shouldn't change the fact that our equation is balanced. All right, now that we've done that piece, we can go ahead and do our stoichiometric calculations. So I'm just going to grab this and we'll bring it over to the next page. Now sometimes, and I'm going to do this here just to make our lives easier, I'm going to calculate the molecular weights for everything, just so we have them ready. And these are all, of course, in grams per mole. So now we can go ahead and run our calculations that we said we needed to. And what we said we were going to do is we're going to start with 11.3 grams of C3H8O and figure out how much oxygen it needs and then how much carbon dioxide and water it'll form. So the first thing we're going to do is figure out how many moles of C3H8O we have. And it comes out to 0.188 moles. And then from here, we're going to have three separate calculations: oxygen, carbon dioxide, and water. We have to do each of those separately. So 0.188 moles C3H8O. And I'm just going to copy this because we're going to use it three separate times. All right, and in the first case, we're going to go to moles of oxygen. And from there to grams of oxygen. And we find that this will require 27.1 grams of oxygen. Our next one will go to moles of CO2. Back to our balanced equation, that means 6 moles of CO2. And then carbon dioxide, we said, has a molar mass of 44 grams. So again, we can do our calculation here. When you think about it, stoichiometry is in many ways just another type of unit conversion. And then finally, we can do our calculation for water. Again, back to our balanced equation, we need now 8 moles of water is what's formed. And that's from 2 moles C3H8O, molar mass for water, 18 grams per mole. Again, do our multiplication here. And we get 13.5 grams of water. One other thing to note, if you think about conservation of mass, we should have the same amount of mass on both sides of the equation. And our amount of carbon dioxide we started with 11.3 grams. So our starting material side had 11.3 plus 27.1. On our product side, we have 24.8 and 13.5. Do those give us the same amount? So 37, 38.3 on the right, 38.4 on the left. So it seems like maybe they're a little bit off, but it's safe to say if we're that close that the difference is based on rounding. So that's how we do this part where we're trying to determine calculations of a product. So these numbers we've calculated here for the products, these would be known as the theoretical yield for the reaction. And by the theoretical yield, that means that's the most product that reaction can form, if it works perfectly. So if it works to 100% efficiency, then we would end up with that much carbon dioxide and that much water. Does that always happen? No, in fact, that happens very rarely, but that's the situation we have. Now, what we'll start and go over in the next video is the idea of limiting reactants. Because we're not always going to have enough of everything that we need. And so the question becomes, based on what we add to a reaction, what will we actually end up with? And which of our reagents actually controls what we end up with?